In this video, we're going to be discussing the chi-squared goodness of fit analysis, including a couple of examples, one that I'll work through and one that we'll have you practice working through. So for this analysis, we're going to compare counts from a single categorical variable, again, our observed counts, the ones that we actually saw in data, to the pre-hypothesized counts, which we'll call expected counts. And again, sometimes these pre-hypothesized values are given as percentages. Now, these pre-hypothesized counts are typically listed in the null hypothesis, where the percentages or proportions, the decimal version of percentages, are typically listed in the null hypothesis. And the alternative is going to be that these pre-hypothesized values are wrong. Again, percentages are often used so that we don't have to have specific counts. Note that if I'm discussing a particular situation, the counts may or may not be correct, but depending on the total number of individuals. So for instance, if I hypothesize 100 will be in a certain group, that might be extremely high if my sample size is only 10, impossibly high. Of course, that might be impossibly low if I'm looking at a national sample of 100,000 participants. So the counts, when we do the pre-hypothesized or expected values, they do have to be converted to counts, but typically we initially make these null hypotheses in terms of percentages so that they're more broadly applicable. So it does involve a conversion here. I will say one common percentage that we can assume for the null hypothesis is to assume that each group has the same likelihood. So for instance, if I have K levels, let's say I have 3 levels of triage, and I'm assuming that each level of triage has the same number of patients that enter it. That's not a very good assumption, right? But just for the sake of argument, then the proportion that I would assume in each group, if I'm assuming they're all the same, is 1 divided by the number of levels in my categorical variable, the number of options. In this case, 3 or 1/3. I'd have 33% in one group, 33% in the other, and 33% in the other. That would be my percentages for each group that I would use as my null hypothesis. Sometimes this type of null hypothesis assumption is called a uniform assumption, referring to the uniform distribution, which just means that everybody has the same likelihood or probability. Now, when we have a percentage and we want to move it to a count, it's actually very straightforward. To get the counts, which are the expected value that we're going to use in the equation we discussed in the last video, we simply multiply the proportion, that's the decimal version of the percentage, by the total sample size for all of the groups. So I might have 10 patients in one, 20 patients in another, 30 patients in another group, for a total number of patients of 60. I would multiply my pre-specified percentage, let's use the percentage we came up with earlier, 1/3, by the total sample size of all of the people in all the groups, 60 total participants, to get my expected value or my expected count in the group to be 20 individuals. I'd expect 20 individuals in the first group, repeat the calculation with a new percentage, which actually is the same because all the percentages are the same, in the second group to get another 20%, and then, to get another 20 participants, 33% again, and then in the last group to get another 20 participants. That would be our expected counts in the null hypothesis and the uniform distribution, assuming every group has the same likelihood. And actually, this is all we need. We already talked about our equation. We already talked about the chi-square distribution and the degrees of freedom and how to find that. So this is all we need in order to actually implement an example. So let's try it. In this case, I'm going to consider an example where I want to study which hospitals patients are going to, and I want to take into account hospital size in terms of staff load. So I don't just want to compare hospital A to hospital B to hospital C and see if they're the same. Actually, I think you'll do that in your problem in just a second. In this problem, what I'm going to do is I'm going to compare hospital A, and then I'm going to look at, and hospital B and hospital C, I'm going to look at how big the hospitals are, again, defining big by staff load, because I don't want to do it by patient. And then I want to see how these compare after accounting for staff load. Like, are some hospitals having a larger amount of patients after taking into account their staff load, or some hospitals having a smaller amount of patients? For hospitals who are having a large amount of patients after accounting for their staff load, maybe they're running lean. Maybe they are, again, able to accommodate more patients than just the staff load would suggest. So to find the proportion of staff loads, I would take each hospital's staff load and divide it by the sum of all of the staff load over all the hospitals. Doing this for 3 hospitals, I find that Hospital A has 43% staff load, Hospital B has 21% total staff load, Hospital C has 36% of total staff load. So this is going to be my null hypothesis, is that my patients are going to follow this, that Hospital A has 43% of the staff load, so Hospital A gets 43% of the patients. Hospital B has 21% of the staff load, so Hospital B gets 21% of patients. And that's what we're going to test in this example. Now here I'm going to use an alpha level of 0.10. Again, it's a one-tailed test. It's just on the right. I'm looking for high test statistics. That's how it's going to be critically over the critical value is where it's going to be statistically significant. And we're going to look to see if the patient load follows these proportions. So first off, we'll go and collect data on the number of patients seen by each of the hospitals. And this is going to be our table of values. Hopefully, where is that darn thing? Oh, there it is. Just took a second to pop up here. So we go in and we can mark down the observed counts within each of the 3 hospitals. 133 individuals went to Hospital A, 52 went to Hospital B, and 89 went to Hospital C. Now we can write out our hypotheses. And we could write out our hypotheses even before finding our data, because we found that from the staff information. But here, our null hypothesis is that the proportion of individuals of the patients in Hospital A is going to be 43%. That's the same as the proportion of staff at Hospital A. Proportion of patients at Hospital B is going to be 0.21, 21%, the same as the proportion of staff at Hospital B. And proportion of patients at Hospital C is going to be 0.36, 36%, the same as the proportion of staff at Hospital C. Now, what's interesting in these tests, and this is going to be true for this test, and I believe the next one we talk about in this class next week, is that the alternative hypothesis, and actually we'll talk about this with the test of independence too, the alternative hypothesis is kind of difficult to represent in equation form. It's that there exists some combination of A, B, and C such that probability of A is not equal to the pre-expected value. But really what we're saying is that at least one of them is different. At least one of these values is different than their pre-specified value. That's what we're saying. And so here, instead of trying to write that out in equation form, I'm just going to write at least one of these is different. And so now that I have my now that I have my proportions, now we can calculate the expected value under the null hypothesis. Remember how we do this. I want to take my null hypothesized value, I multiply it by the total number of patients I have in my sample. So in this case, I have 133 plus 52 plus 89, 274 patients. And that gives me my expected value, 117.82. You'll note this is not a whole number. This is not a real number of patients that I could have in Hospital A, but this will serve as my expected value, decimal and all, for this particular cell. Then I do the same thing for Hospital B, but now with the Hospital B's pre-specified proportion of 21% multiplied by the total sample size. Again, how many people do I have in my study? 274. And multiply by 274, and that gives me my expected value here, 57.54. And then I would do the same thing for Hospital see. Now, I do want to pause for a moment and consider this because at this point, we could type this information into a statistical software program to run the analysis. In fact, where we can type it in is I could type it in at the point where I have my data and my null and alternative hypothesis. I wouldn't have to calculate those expected values by hand. I could stop after I have my null and alternative hypothesis and with my data, and I could type it in there. So I want to pretend we did this and look at some output from a computer program that ran this analysis. So I went ahead and ran this analysis in a software called R. This is the output I got back. And I want you to think through how would you interpret this output. So this is kind of a common question. Hey, what do we do when we actually run this? And when we actually run this, we rarely calculate the expected values by hand. It's good to know what we're doing, and we're still going to work through that in the rest of this lecture video and lecture set. But honestly, what often happens more is that I have my observed values, I have my pre-specified null hypothesis percentages that I want to test, and I plug those into a computer and I say, run it. And it does. And it gives you back this. And I mean it. This is the only thing that the software gives back is just this information. I copied and pasted the entire output from the analysis. And this is all there is. It is 3 lines. The first one is the name of what it did. The second one is the data set, or what I call the data set that I used. And the third one is a summary of 3 statistics. So let's go through these. So what do we have here? Well, the first thing we have is the chi-squared test statistic. That's what we're going to calculate in these notes in just 1 second. That's 3.4313, and actually it'll be a good way to double check our hand calculations in a little bit, is to make sure that this is matching with what we get. We also have the degrees of freedom, which again we can calculate and make sure. I will say I actually quite like the practice of calculating degrees of freedom by hand because it's a really good double check on the software. That degrees of freedom formula is relatively simple. It's the total number of rows minus 1 times the total number of columns minus 1 multiplied by each other, or in this case, it's just the total number of columns minus 1. So I can really quickly check this and make sure that it looks right. There have been probably over a dozen professional situations where a quick check of degrees of freedom indicated that an analysis was providing the wrong feedback. Either an incorrect variable had been interpreted, or the statistical software had read in the data inappropriately, but for whatever reason, the analysis was not giving me the information I wanted. And again, one of the biggest, quickest, best ways that I know to check that is to look at this degrees of freedom value. The last thing that we have here is the p-value. And if you recall from our previous conversations on p-value, a p-value can be used to make a decision with regards to a hypothesis test, and frankly, often is. You'll note that I do have the name of the distribution, the degrees of freedom, and I can go and look up a critical value for the chi-squared distribution with degrees of freedom of 2 to compare this test statistic to, which is the way that we're about to look at this information. But recall, if I have the p-value, I don't need to do any of that work. I can just compare the p-value to my alpha level to know what the decision is. So let's take a moment to remember how we can use this p-value so that we can make a decision without doing the extra work. And again, this is often what we do in practice because we have access to statistical software, which gives us output like this. So recall, if p is greater than alpha, we fail to reject the null hypothesis. So consider one more time, what is the null hypothesis? The null hypothesis is that the proportion of patients matches the proportion of staff at the hospital. If we fail to reject that, that means we don't reject, that we essentially go with that. That's our running hypothesis. That's where we started from. And we didn't have evidence to challenge that, or enough evidence to challenge or make us shake that default belief. The reason we don't accept that is through the acknowledgement that this was our default belief to start with, and we didn't really provide any evidence for that default belief. We just stated that it's our default belief. So we're sticking with our default belief that the proportion of patients match the proportion of staff if P is greater than alpha. So that's what P greater than alpha means. The second case was if P is less than alpha. In that case, we reject the null hypothesis and go with the alternative. Recall the null hypothesis, proportion of patients matches the proportion of staff. If we reject that, we say the proportion of patients we have reason to believe doesn't match the proportion of staff, so we go with the alternative. There is at least one difference. At least one hospital has a different proportion of patients than it does its proportion of staff. And that's the conclusion we would ultimately go with. Now, you can think through both of these interpretations ahead of time, and actually it's usually a good practice to do this. For any given situation and research question, think, what does it mean to reject the null hypothesis? And recall that when we reject the null, we call that statistically significant. What does it mean to have a statistically significant finding here? And what does it mean to fail to reject the null hypothesis? We'll call that not having a statistically significant finding. So what does it mean to not have a statistically significant finding here? We can do that without ever looking at data. All we need to do to check that is to consider the research question and how it's phrased. Here, with alpha equals 0.10, given in our previous slide, we can see that P is greater than alpha. Looking at my notes, I see that that implies I should fail to reject, and remembering the notes that I just took down from Dr. Florin's little diatribe, I can see that that means I am stuck with my default belief. That is, I am stuck with the belief that the proportion of patients, or the number of patients, is proportional to the number of staff at the hospital. Again, the conclusions here with the p-value are the same as the conclusions we would have with the critical value. So we'll talk about that in a second after we finish our doing the work of calculating out this chi-squared test statistic ourselves and comparing it to the critical value. But here from software, I can go on and make that decision. I can jump to the interpretation stage based purely on this p-value, and I can, again, make that decision. Now, I am forced here, and we're going to move on in just a second, I promise. I'm forced here to pause and remind you, when I say I can jump to the conclusion stage, I can jump to the conclusion stage of the inferential statistic. I can't jump to the conclusion stage of the statistical story, and recall the difference and distinction there. The inferential statistic is part of the statistical story. So I can jump to the conclusion of the inferential statistic. What is that evidence providing? But remember, this, in a broader picture, is just one piece of evidence. I'd also look at things like study design, also look at things like effect size, also look at things like graphical summary and descriptive statistics to paint the broader picture of what this piece of evidence means in my story. All right, so let's move on to our calculations. So we're going to run the test statistic using the formula, make sure the software isn't lying to us, and then compare to the critical value. So recall this was our equation. I'm going to take each of my observed values, that was 133, 52, and 89. These are each of my observed values, and subtract their respective expected values. And this is important. You need to subtract the ones that they're matched with, and then divide by their respective expected values. Ultimately, this is getting some measure of distance between the data value and its expected value. Now, I will note when you work this out, all these are going to be positive because all the differences are squared, but I can quickly look at these differences and I can see Hospital A has a patient load that is higher than expected. Hospital B has a patient load that's lower than expected, and Hospital C also has a patient load that's lower than expected. So you can calculate this out specifically, but remember the higher and lower is going to be lost when you square the numbers because of Squaring the numbers will get rid of the positives and negatives. But if you just look at the values and compare the observed counts to the expected counts, you can see which ones are higher, which ones are lower. And actually these, this kind of intermediate step here, the second step, is where we can see where the biggest differences lie. So I can see here that the first part, this hospital A, seems to be the biggest difference contributing to my chi-square statistic. Hospital B seems to be the second biggest difference, but not really as big as the first one. And hospital C seems to be kind of in the middle there. I should mention this interpretation that I'm writing out now. I don't interpret this and I don't write this. I don't describe, hospital A has the biggest difference. Like, I don't talk about that unless there's a statistically significant difference, in which case I might expound on that a little bit later. But I don't talk about the nature of the difference until I know that there is a difference in the story. In any case here, working out the final test statistic value, I work it out to 3.4313. which, thank goodness, the software was correct, and it looks like we match what that got. So now I have my test statistic. I simply compare to the critical value. Notice that I'm using an alpha of 0.10 here. My degrees of freedom is 2, so it is the total number of options. In this case, I had 3 options: hospital A, hospital B, hospital C. And then I subtract 1 from that, and that gives me my degrees of freedom. And if I look this up in a table or in the back of the book or in software, I get 4.6052 for my critical value. Again, our chi-squared uses the upper tail cutoffs, so I'm looking for larger test statistics than this. Our test statistic was like 3.4, so our test statistic is lower than this. It is not significant. We don't have enough evidence to reject the null hypothesis, and we don't have enough evidence to challenge our default belief that the patient load for hospitals in the region differ from what we would have expected based on the proportion of staff. That is, don't have enough evidence to conclude that the proportion of patients doesn't match. Or excuse me, don't have enough evidence to challenge the claim the proportion of patients matches the proportion of staff. We can't challenge that with this evidence. Going back to our subtext of our question, is hospital A, our hospital, running leaner? There's not really enough evidence to determine that. It's not. It seemed to be running a little bit leaner, right? So, but when we looked at the specifics, but it's not there. We don't have enough evidence to believe that in the population. Now, I do want to talk about this because what I just said, it seems to be running a little leaner. Like that claim, that's a really, really bad one. When I'm writing this up here, this is what I include. I don't include that claim. I don't say there seemed to be evidence that it was running a bit leaner. And in the sample, it was running leaner. That's true. On the other hand, here's the thing. Remember that without statistical significance, I don't have the evidence that any of those differences between the hospital and their expected value is different than 0. The statistical test, the inferential test, tells me if there's evidence to believe that in the population. And here, I don't have evidence to believe that in the population. Again, I'm making a claim. There's not enough evidence to determine that there's a difference. So I can't say, yeah, we were running a little leaner, but then on the other side of my mouth say, yeah, but we don't have enough evidence to think that we're running leaner. Were we to include that interpretation, this is confusing to our readers. And again, remember the purpose of this. This is to contribute evidence to a story. And so when we do something like discussing how hospital A is running leaner than the others as shown in the previous slide or whatever, this is kind of directly contradicting what our test is. Now, we, because we've been through this stats class, understand the difference, that it is leaner in the sample, but we don't have evidence to know that this is leaner in the population. But in trying to tell our statistical story and in thinking about the audience that we're telling this story to try to introduce both of those claims is really just going to confuse the issue. And if I'm presenting this to a group of individuals who want our hospital to be running leaner, they are going to latch on to the statement, well, we are running a little leaner in our sample, and just ignore the statement, but we don't have enough evidence to determine if this is true for the population. So it's very important to present a story in a way that actually tells the story. Otherwise, it kind of feels like talking out of both sides of our mouth a little bit. If we start discussing how Hospital A was running a little bit leaner and then say, yeah, but our stats test says we don't have enough evidence to determine Hospital A is running a bit leaner. So because of this, long story short, when we don't find a statistically significant difference, we don't often talk about the distinctions between the values in the sample. So again, in the previous slide I showed, hey, Hospital A is running a bit leaner. It seems to be a more massive effect than either Hospital B or Hospital C. I think it was at least twice the size of the effect as in Hospital B or Hospital C. But I'm not going to talk about that because the inferential test for the population says, hey, we don't have enough evidence to think that there's a difference. Even for Hospital A, remember our null versus alternative. Our alternative was any of them are different. And here we're saying, yeah, even for Hospital A, we don't have the evidence to determine that Hospital A is different than that is different than that pre-specified value, that Hospital A is running leaner. It's getting more patients than we would have expected based on the proportion of staff it has. We don't have enough evidence to make that claim. And so if we don't have enough evidence to make that claim, I'm not now going to spend, half an hour expounding on how in our sample, Hospital A is way leaner, blah, 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 blah. In fact, I'm not even going to mention it. I'm not even going to breathe it, because if I do, again, thinking about your story, that's going to compromise your story. It's going to create confusion in your story. There's a couple of exceptions to this, but as a broad rule, again, if you don't find a statistically significant difference, you don't then talk about the size of the difference between the groups, because you don't have evidence that there's any difference between the groups. And a subsequent conversation on the size of the difference between the groups contradicts your own story that we don't know that there's any difference at all. All right. So now it's your turn. We're going to do the same problem with the same data, but we're going to look at it through a different lens. Let's say we have a coworker who also has an explanation for the number of patients at the hospitals. Let's say that coworker says each hospital gets the same number of patients. That is, the hospitals are uniformly distributed in the number of patients they receive. For the same data and the same cutoff value, I want you to test this hypothesis. So go on, pause the video. In fact, I'll go pull up the data for you if I can. Here's the data. So go on and pause the video right now. Take a moment and give this one a shot on your own, testing against that default belief that every hospital gets the same number of patients, that uniform distribution for the null hypothesis, and see how you do. And then, so pause the video, then come back when you are good to go. Go, go, go. All right, so coming back, I hope that went well. Our null and alternative hypothesis. So the null hypothesis for the uniform distribution is going to be that I have 3 groups, each are evenly balanced, and we said if we're doing that, we take 1 divided by the number of groups. So 1 divided by 3 gives me 0.3 repeating. So that's going to be my three values. And if you wrote 1/3 here, that's fine. It doesn't have to be in decimal form or anything. It's the mathematical quantity that's important. It's not the representation of it. So don't worry about that. Again, the alternative is at least one of these hospitals is different than that proportion of patients. From here, I can go on and find my expected values. So I get the expected values to be 0.3 repeating times 274 patients, which is the same as before. That gives me 91.33 patients that I expect for hospital A, B, and C. And it's the same calculation because the proportions are the same. The second part of the equation is the total sample size, which doesn't change. So I end up getting the same number, 91.33 for each one. Calculating this out, the test statistic is going to work out to be 36.007. When I work out the test statistic, again, I take the observed minus the expected, raise it to the second power, divide by the expected for each one of these hospitals, and then I add it all up. Finally, we compare to the critical value that we had before. Again, we're using an alpha of 0.10. The degrees of freedom, which is the number of groups minus 1, has not changed because we're still dealing with 3 groups. So our critical value hasn't changed, 4.6. On the other hand, our test statistic was now in the 30s. This is far above our critical value. So there is definitely enough evidence to reject this null hypothesis. That is, we do have enough evidence to determine that the patient load for the hospitals in the region are not equivalent to one another. Again, note the power of inferential statistics here. This is not just for the weeks that we looked at, right? So this is overall for hospital A, B, and C, not just for the time period that we studied, but overall for all of the hospitals that are represented by that time period at the times that are represented by that time period. So this is the power of inferential stats. Is it a sure thing? No, but we're reasonably confident in this. What does reasonably confident mean? Well, it depends on the alpha level. In this case, because alpha is 0.10, reasonably confident means 90% confident or better. Now, I should make a couple of notes here. We came to a different conclusion here than we did previously. So my first note is the difference here isn't the data. The data are the same. The difference is the null hypothesis. And this actually leads to a bigger point in statistics. Often in applied research, you'll say researchers, especially somewhat jaded ones, will talk about how the goal is statistical significance. But what I want to point out that we can see here is in one, we found a statistically significant difference, and the other we didn't, and we have the same data in both. The significance conclusion is only meaningful if the hypothesis, the null hypothesis you're testing, is meaningful. Again, think about the statistical story. Both of these have the same data, but provide different evidence because they're contributing to different stories. The first one was telling a story about a patient load compared to staff load and didn't find that there was a difference in the population. Remember, this is how inferential stats contributes to the story, is it makes the conclusions about the population, and we didn't find that in that first story there was a difference in the population. This test is telling a story about patient load being evenly distributed. And we did find that that default belief isn't very compatible with the data. And because of this, we believe that the population of patients going to these hospitals is not evenly distributed based on the evidence from this inferential statistic. So our significance and inferential statistics always provide evidence regarding the story and within that context. The story being what's listed in the hypotheses. And this is why the hypotheses are important, because it details what evidence the inferential statistics are providing, or what story the inferential statistics are providing evidence for. So don't think of statistical significance as meaningful in and of itself. Think of them as meaningful as parts of the story. All right, so let's do the computer report for this one that we just had. Again, running this, this is what it spits out. We can confirm that this is the chi-squared value that we just calculated by hand. And then we can also confirm our decision for the test. So here, because p is less than alpha, we would reject the null hypothesis and go with the alternative. And again, the interpretation is the same as before. The p-value approach versus the critical value approach, those are different ways to make a conclusion about do we reject or fail to reject the null hypothesis. That is the outcome of the p-value approach or the critical value approach. Everything else is the same for the two. That's the only contribution it makes. And then the rest of the interpretation is identical between them. I'll note here the p-value might look a little bit weird in this software, e to the negative 0.8. This implies this is times 10 to the negative 8 power, or we move the decimal place to the left 8 spots. And all of these others are 0. So this is 0.00000000157. So a very small number for the p-value, which is why p is less than alpha. P is a very small number. Again, that indicates compatibility in a way between our data and the null hypothesis. This implies that these are very incompatible with one another, certainly less than our threshold, and indicates that we should get rid of that null hypothesis because the data is not compatible with it. So when we get rid of the null hypothesis, we end up going with the alternative. And again, the alternative, at least one hospital's patient group is different than the null. In this case, our null was they're all the same. So we're saying at least one hospital's patient group is different than the others. All right, well, this has been our discussion on the chi-squared goodness of fit test. In the next video, we're going to be discussing the chi-squared test of independence.